trying to find the mass, or the total mass, I'll call it, and the center of mass. And we're given that it's made of these two materials. It's the steel, and we're given its density. So I'll put that there. The steel is 7.85 megagrams per cubic meter. And for the brass piece, it's more dense, 8.74 megagrams per meter cubed. All right, I'm going to begin the same way we looked at the last ones. I want to put this figure, and then I'm going to determine how to break it up into the smaller shapes so that I can fill out my table. And I'll stick with the coordinate system that's given in the problem. Okay, so we see that kind of bottom right corner of the object is at the origin. B is going to be the brass piece, and A is going to be the steel piece here. So we have 3D shapes here that we need to break this down into. And simple shapes are going to be better to use than more complicated ones. So shape A, what we have here, it is a trapezoid. And we could treat it as such, but I think it's going to be easier to break it down instead of worrying about how to find the area or the volume of a trapezoidal solid, is just have more simple shapes. So I would say for this one, I'm going to break A up into a rectangular piece and a triangular piece. So A I'll actually make two shapes out of, and B is already a triangular solid. I'll just leave it as that. So we do have a uniform depth of 30 millimeters. This is 150 millimeters, and that's also 150 millimeters, and 225 millimeters tall. Yeah, I mean, it's not a free body diagram, but we want to draw it because we want to say, so for example, I'm going to put this into 3 shapes here. So I want to make sure that I've labeled that, and then when I make the table, I know which shape I'm referring to and where. And then since I split this top shape, or shape A, into this triangle and then this rectangle, I want to know what the base of this top triangle is going to be. That will also have that base of 150 millimeters. Okay, so shape 1 is a rectangular solid. Shapes 2 and 3 are triangular solids. But shape 1 and 2 are made of the steel, and shape 3 is going to be made of the brass. 3 shapes, and then I have the summation I'll take at the bottom. Because this is 3D, each shape is going to have a volume, not just an area associated with it. And for my notes, I kept everything in meters to the 3rd power, I guess I used. I will need the density of the different shapes, which I'll just keep in megagrams per meter cubed, since that's what was provided to us. And then we'll be able to compute the mass of each shape by multiplying its volume by its density. And now I need to find the centroid location of each of my shapes, and I'm going to keep these in meters. Then I have to have the last 3 columns. I'm multiplying the mass times each of my centroids. So just an extended version of the tables that we looked at on Friday. Shape number 1, I labeled as this rectangular solid piece here. So its volume is going to be its height times its base times its depth. So 225 millimeters by 150 millimeters by 30 millimeters. And for my table, I put everything in meters cubed. So I would convert this to 0.225, 0.15, and 0.03. But if you kept everything in millimeters cubed, that would be okay, as long as your units are all going to be consistent with each other in the end. I have 0.225 times 0.15 times 0.03. That's 1.01 times 10 to the negative 3rd meters cubed. For shape 2, I have that triangular solid. So if I find the surface the area of the triangular piece and then multiply it by its thickness. Then I'll have the volume for my second shape for this triangular solid. It has a height of 225 millimeters. It has a base of 150. And it has a thickness of 30. So the surface area will be 1/2 its base times its height. And then I multiply that by its thickness of 30 millimeters. So shape 2 is going to have, that has the volume of 5.06, -4. And shape 3, my other triangular piece, has the same dimensions as shape number 2, so therefore its volume is also the same. So even though the shapes 2 and 3 have the same volume, because they're made of different materials, their masses will be different in that step. So for shape 1, 2, and 3, I have to put the associated density that's related to that material. So shape 1 and 2 are both made of the steel, so they will both have the same density of 7.85. But shape 3, made of the brass, has the higher density, the 8.74. Notice again for this center of mass type of problem, I could find the total volume if I wanted to, but the important thing here is to find that total mass, because that's what I'm going to divide the mx tilde, my tilde, mz tilde by later in order to find the x bar, the y bar, and the z bar for the center of mass of the object. If this was all one material, this would be a very easy problem because I would just treat it as that rectangular solid. So to find the centroid of this is easy. To find center of mass, we have to go through this more involved step. The mass of each of these shapes is just going to be its volume times its cubic density. So for shape number 1, it has a mass of 7.95 times 10 to the negative 3 megagrams. For shape 2, when I multiply that, I get 3.97 times 10 to the negative 3. And for shape number 3, I get 4.42 times 10 to the negative 3. And now summing down that column, the total mass of my object, 1.63 times 10 to the negative 2 megagrams, is the weight, the mass of this. Now it's going to look familiar to what we saw before, but we have to find x tilde, y tilde, and z tilde for each of these shapes. So the same rules basically apply for a rectangular solid or the triangular solid that we saw for the 2D shape. So for shape number 1, it's x tilde. Measuring from the origin, we have to go by half of its base. So it's 150 millimeters total. So half of that will be 75 millimeters in the positive x direction. So for that shape number 1, I get 0.075 for meters. For shape 2, I have this right triangular solid. So I have to go 1/3 of its base from its right angle to find the x direction for its centroid. So that's going to be 50 millimeters, but from the origin, I have to go all 150 and then an additional 50 from the origin to get to the x centroid for shape number 2. So I have to go a total of 200 millimeters to get there. So I get 0.2 for that shape. And for shape number 3, again, a right triangular solid. I have to go 1/3 of its base away from the right angle, so that dimension's 50. So I have to go 150 millimeters and then another 100 millimeters. So 250 millimeters or 0.25 in the x direction. In the y direction, this one's actually pretty simple because they have uniform thickness here. Each one of these shapes is going to be half of its thickness, but in the negative y direction. So 30 millimeters, half of that is going to get me the y centroid for all three of my shapes. So 15 millimeters or 0.015. And it's negative because it's in the negative negative y direction. And now the z tilde, because we're in 3 dimensions, for shape number 1, I have to go to half of its height from the origin. So 225 divided by 2. So in the z direction, shape number 1, I get 0.113. For shape 2, 1/3 of its height away from its right angle. So that is going to be 1/3 of 225. So as measured from the origin, 2/3 of 225 will be the z centroid location for my shape number 2. So 2/3 of 225, I get about 0.15. And finally, shape number 3, 1/3 of its base. I now have to use 1/3 of 225 as measured from the origin to get to its z centroid. So shape 3, I get 0.075. Yeah.
Why did we divide that by 1/3 to find x for the second shape?
For the second shape, because in this direction it's a triangle. So the right triangle is 1/3 of its base and 1/3 of its height from the right angle to get to its centroid. So for the rectangle, it's just half the height, half the base. But right triangles, 1/3 of its base, 1/3 of its height, gets you to where its centroid is. Questions to this point. This is really the point where you have to do the work. You have to look at the figure to determine what all these are. The next part, we're really just doing multiplication, and all the numbers are already down for us. If we multiply the m and the x tilde, we'll go and get all of those values. I'll just put in the final results here. You multiply those out, and we add them together. I'll just put those numbers up. We get 2.5 times 10 to the negative third as the total for mx tilde. Negative 2.45 times 10 to the negative 4 for my tilde. And 1.82 times 10 to the negative 3 for mz tilde. And then those steps in between, but you can multiply that out. The last step then, I want to find my x bar, y bar, z bar. Basically the same thing we did before. I take my total mx tilde and divide that by the total mass. My x bar then, 0.15 meters. My y bar, I'll take the negative 2.45 times 10 to the negative 3 over 1.63 times 10 to the negative 2. Now I get negative 0.015 meters. And since that was the centroid for each of my shapes, then that should be the centroid for the entire shape also. And then the z tilde, 1.82 times 10 to the negative 3 over that total mass of 1.63 times 10 to the negative 2. Z tilde, I get about 0.11 meters as its value. All right, so what does it say? If we start at the origin and we go 0.15 in the x direction, and then we go up in the z direction by 0.11, so that's less than half of its height. Then we see that our center of mass is not located, as we should expect, not located at the centroid, which would just be half of this base and half of this height. So the fact that we have the brass here is kind of, with our weighted average, pulling the center of mass down because there's more brass below the halfway point than there is above the halfway point. So the center of mass, not the same as the centroid in this case, because they're made of those different materials.